Module 7, Lecture B, Backpropagation Basics. By the end of this lecture, you will be able to explain backpropagation as distributing output error backward through network layers, implement a simple neural network training loop with manual gradients and NumPy, and analyze neural network learning using loss curves, test metrics, and overfitting checks. Gradient flow. Output error. Output error is the starting signal for learning in backpropagation. After a neural network makes a prediction, the loss measures how far that prediction is from the target. This error shows how the final output should change, such as reducing confidence in a wrong class and increasing it for the correct one. In this way, it identifies the gap between current behavior and the desired result. Output error gives a neural network the numerical feedback it needs to learn. It shows how the final prediction contributed to the loss, such as the gap between predicted probabilities and the correct class in classification, or the difference from the target value in regression. This turns the task goal into a concrete training signal, which can then be traced backward to identify earlier decisions that led to the mistake. Backpropagation starts with the output error and sends that information backward through the network. The final layer receives the most direct feedback, but earlier layers also share responsibility because they helped produce the prediction. By tracing how each weight and bias influence the error, the network creates gradients that guide the internal adjustments needed for learning. Python code, output error. The output error is the starting point for gradient flow through the network. In this tiny model, the network predicts beam deflection, and manual gradient calculations show how each weight shares responsibility for the final error. The script begins by importing two key Python libraries, NumPy for efficient numerical work with arrays and mathematical operations, and Matplotlib's plotting tools for creating visualizations. Together, these libraries prepare the script for data processing and visual display. To make results repeatable, we set a fixed seed for NumPy's random number generator. Using the seed value 7 ensures the same random sequence is produced each time the code runs, which helps with debugging and comparing results across runs. We create a small training dataset for a mechanical engineering example. It pairs applied loads of 1 to 4 kilonewtons with measured beam deflections of about 2 to 8.2 millimeters. This data will train a tiny neural network to predict deflection from the applied load. To keep training stable, the input and output data are scaled to smaller ranges. Load values in kilonewtons are divided by 4, and true deflection values in millimeters are divided by 8.2. This improves numerical stability and helps prevent problems such as exploding gradients. Before training, check that the input data and target data have matching shapes, so each input has a corresponding target. Also confirm there are exactly 4 samples, which helps verify the dataset is structured correctly and avoids training errors. The neural network parameters are initialized for 1 input, 1 hidden layer with 3 neurons, and 1 output. The input to hidden and hidden to output weight matrices are filled with random values from a normal distribution with mean 0 and standard deviation 0.4. The hidden layer bias is set to zeros for its 3 neurons, and the output bias is set to 0 for the single output neuron. We create a list to record the mean squared error after each training epoch so we can monitor the model's learning progress. We also set the learning rate to 0.35, which controls how strongly the network's weights are adjusted during training. The training loop runs for 120 epochs. In each epoch, the network performs a forward pass by computing the hidden layer values from the inputs, weights, and bias, then applying the hyperbolic tangent function for nonlinearity. It then produces predictions using the hidden layer outputs with a second set of weights and bias, preparing for error calculation and weight updates. Training performance is measured by first finding the difference between the model's predictions and the true values. These errors are squared and averaged to produce a single loss value, showing how far off the model is overall. This loss is then recorded for each training epoch, so progress can be tracked over time. To update the second layer, we first find how the loss changes with the model's predictions by scaling the output error by the number of samples. Then we use the hidden layer activations and this prediction gradient to determine how the second layer's weights should change. Finally, we sum the prediction gradient across all samples to get the bias gradient, helping reduce the overall error. Backpropagation first finds how the hidden layer affects the loss by combining the prediction error with the second layer's weights. Because the hidden layer uses the hyperbolic tangent activation, this gradient is adjusted using the derivative of that function. The adjusted gradient is then used to compute how the first layer's weights and biases contribute to the error, so they can be updated during training. The code trains the neural network by using gradient descent to update its weights and biases. For each layer, it subtracts the learning rate times the corresponding gradient from the current parameter values. Repeating this process adjusts all parameters to reduce the loss and improve the network's performance. The network first computes the hidden layer's raw values by combining the inputs with the first weights and biases. It then applies the hyperbolic tangent function to add nonlinearity and produce the hidden activations. These activations are combined with the second weights and biases to make final predictions, and the output error is found by comparing those predictions with the true values. The neural network's scaled predictions are converted back to millimeters by multiplying them by 8.2, reversing the earlier normalization. The output errors are scaled the same way, so both predictions and errors can be interpreted in real-world units and compared with the true measurements. The output first reports the NumPy version to support compatibility and reproducibility. It then compares the model's initial and final loss to show how training reduced error, and gives the last error in millimeters as a practical accuracy measure. This final output error also provides the starting signal for backpropagation, which updates the model's parameters. This plot shows how the model's mean squared error changes across training epochs. A clear line chart is created with labeled axes, a descriptive title, and a light grid to make the trend easy to read. The main purpose is to visualize whether the output error decreases during backpropagation, indicating learning progress. This script trains a small neural network to predict beam deflection from load data using manual backpropagation. The data is scaled for stable training, and the network updates its weights and biases over 120 epochs to reduce mean squared error. As training progresses, the loss decreases, showing that the predictions improve. The final error is converted back to millimeters, and the printed results and loss curve summarize the network's learning progress. Hidden layer gradients. Hidden layer gradients show how much each internal layer contributed to the network's error. Backpropagation starts with the error at the output layer and works backward, estimating how hidden units influenced later layers. This lets the network adjust earlier layers so it can reduce future errors. In a neural network, hidden neurons pass information forward through weighted connections, helping shape the final prediction. During backpropagation, error signals travel backward through those same connections. Neurons that strongly affect an incorrect output receive stronger gradient signals, showing how sensitive they are to change. These signals guide parameter updates, so the network can learn more effectively. Hidden layer gradients let deep networks improve their internal feature detectors, not just adjust the final decision layer. In a classifier, hidden layers learn useful features, such as strokes and number-like shapes in digit recognition, while the output layer uses those features to make a decision. When the network makes a mistake, the error is sent backward, so both the features and the decision boundary can improve, even though this signal can become distorted in very deep networks. Python code, hidden layer gradients. Hidden gradients show how output error is passed backward through a small neural network. In this example, manual NumPy calculations reveal how responsibility for the error reaches the hidden units. The code starts by importing NumPy for efficient numerical work with arrays and mathematical operations. It also imports Matplotlib's plotting tools to visualize results, such as a training loss curve. Together, these libraries prepare the environment for neural network computation and visualization. We use NumPy's random module with a seed of 7, so it produces the same random numbers each time the code runs. This makes results reproducible, which is especially useful for teaching and debugging. A small dataset is created to represent simple binary sensor readings. It contains 4 input pairs, covering all combinations of 0 and 1, along with matching target outputs that follow the XOR pattern. This gives the neural network the basic input and output data it needs for training. The code verifies that the input data has the expected shape before training. It checks that the feature data contains 4 data points with 2 features each, and that the target data contains 1 value for each point. These checks help catch shape mismatches early and prevent training errors. The 2-layer neural network is initialized by setting random weights and 0 biases for each layer. The first layer uses a 2x3 weight matrix, and the second uses a 3x1 weight matrix, both drawn from a normal distribution centered at 0 with a standard deviation of 0.8. Random weights help break symmetry during training, while 0 biases ensure the network starts without any initial bias influence. The sigmoid activation function transforms an input into a value between 0 and 1. It does this by taking 1 divided by 1 plus the exponential of the negative input. Because it bounds outputs in this range, sigmoid is commonly used in neural networks, especially for binary classification and stable training. The sigmoid gradient function finds the slope of the sigmoid output by multiplying that output by 1 minus itself. This gradient is used during backpropagation to show how much each weight affects the error, helping the neural network update its weights. We create an empty list to record the loss after each training epoch, so we can monitor how the model improves over time. We also set the learning rate to 0.8, which controls how large each weight update is during training. The network is trained over 1,200 iterations. In each pass, the input data is combined with the first weights and bias, then passed through the sigmoid function to produce hidden layer activations. These activations are then combined with the second weights and bias, and another sigmoid function produces the network's predicted outputs. The code measures prediction error by comparing predicted values with the true targets. It then squares these errors and averages them to produce the mean squared error, a single loss value showing overall model accuracy. This loss is saved each training epoch, so the model's learning progress can be tracked. Backpropagation for the second layer starts by scaling the prediction error by the number of samples to get the loss gradient. This gradient is then passed through the sigmoid derivative to account for the output activation. The weight gradient is found by combining this result with the hidden layer activations, showing how each hidden unit contributed to the error. The bias gradient is computed by summing the output layer gradients across all samples while keeping the correct dimensions. Backpropagation through the hidden layer starts by sending the output layer error backward through the transposed hidden to output weights. This gives the gradient for the hidden activations, which is then adjusted by the sigmoid derivative to find the gradient for the hidden pre-activation values. From there, the input to hidden weight gradients are found by combining the input data with these pre-activation gradients. And the hidden bias gradients are found by summing them across all training samples. The code uses gradient descent to update the neural network's parameters. It adjusts the weights and biases in both layers by subtracting the learning rate times their gradients. These updates move the parameters in a direction that reduces the loss. The model turns its continuous predictions into binary classes by checking whether each value is at least 1/2 and then converting the result to integers. It also summarizes gradient activity by averaging the absolute gradient values in the hidden layer and in the output layer. These two averages give simple measures of the signal strength contributed by each layer. The output summarizes key training results: the NumPy version for reproducibility, the final loss to show learning performance, and the predicted classes for the model's classifications. It also reports the average gradient signals at the output and hidden layers, which indicate how strongly errors are driving learning. The hidden gradients come from the output error being passed backward through the second layer's weights, illustrating the basic backpropagation process. This code creates a plot to show how training loss changes over epochs. It draws the mean square error as a clear navy line, labels the axes, and adds a title describing the manual backpropagation loss curve. A subtle grid and adjusted layout make the graph easier to read before it is displayed. This script builds a simple two-layer neural network in NumPy to learn the XOR classification task using sigmoid activation and manual backpropagation. During training, it updates weights and biases to reduce mean squared error, and the falling loss shows that predictions improve over time. The final results report the last loss, predicted classes, and gradient signals, including hidden layer gradients that show how error is passed backward through the network. A loss curve provides a visual check that the model is learning. Chain rule. The chain rule makes backpropagation possible by showing how changes in earlier layers influence the final output. When a neural network makes an error, backpropagation uses the chain rule to trace that error backward and estimate how much each weight contributed. By combining these effects layer by layer, the network can adjust its parameters and improve future predictions. Backpropagation uses the chain rule to trace an output error back through a neural network. The loss shows how far the final result is from the target, while gradients indicate how much each earlier weight contributed to that error. The chain rule keeps these responsibility signals accurate, so the network can adjust each weight according to its true impact. The chain rule is essential in deep neural networks because it lets error signals move backward through many layers, so each layer can adjust its weights based on how it affected the final loss. This allows both early and later layers to improve when predictions are wrong, but gradients can become too small or too large, making learning slow or unstable. Understanding this gradient flow helps explain how networks learn and why activation functions and depth matter during training. Python code. Chain rule. The chain rule shows how responsibility for an error flows backward through a small neural network. By computing each local derivative with NumPy, we can trace how gradients move from the output back through earlier steps. We import NumPy to handle efficient numerical work with arrays and matrices. We also import Matplotlib's plotting tools to create visualizations that help present data and results clearly. A fixed random seed is set with NumPy using the value 7, so the code produces the same random results each time it runs. This makes the output deterministic, which helps with debugging and testing. This example sets up a simple mechanical sensor reading. To illustrate error calculation for backpropagation, the sensor input is represented as a two-dimensional array with the value 2, while the expected output is a one-dimensional array with the value 1. Comparing the predicted and true values provides the error needed to understand how the chain rule is used. Two weights are initialized for a simple neural network. One weight, set to 0.4, connects the input to the hidden layer, while the other, set to 1.5, connects the hidden layer to the output. During the forward pass, these weights are used in matrix multiplication to help compute the network's prediction. A forward pass computes the network's output in two stages. The input is first combined with the first set of weights to produce the hidden layer output. That hidden output is then combined with the second set of weights to generate the final prediction. To measure prediction error, subtract the true value from the model's predicted value. The squared error loss is then found by taking half of that error squared, which emphasizes larger mistakes and gives a smooth signal for optimization. For backpropagation, we compute key derivatives that show how the loss changes through the network. The loss changes with the prediction by the amount of the error. The prediction changes with the second weight according to the hidden layer value. And the prediction changes with the hidden layer according to the second weight. Together, these derivatives guide how the weights should be adjusted to reduce the loss. In the backward pass, we compute how each weight contributes to the loss. The hidden layer's derivative with respect to the first weight is based on the input, showing how the input affects the hidden activations. The gradient for the second weight comes from combining the hidden layer with the loss derivative at the prediction. The gradient for the first weight then applies the chain rule, tracing the effect from the input through the hidden layer and prediction to the final loss. We check that each weight gradient has the same shape as its corresponding weight matrix. These shape checks confirm that the gradient calculations are dimensionally consistent and help catch mismatches early, supporting correct backpropagation. The code reports the model's prediction, the loss, and the gradients for the two weights, each rounded to 3 decimal places. These values show how far the prediction is from the true value and how each weight should change to reduce the loss. It also briefly explains that the gradient for the first weight is found by using the chain rule to pass the error backward through the network. This visualization tracks how the error signal moves backward through the network during backpropagation. It begins with the output error, then shows the gradient passing through the second weight, and finally shows it reaching the first weight. The corresponding values represent the initial loss gradient, the gradient after passing through the second weight, and the final gradient used for the first weight. This plot uses a bar chart to show how the gradient signal moves backward through the chain rule process. Each bar represents a stage of the gradient flow, with different colors helping separate the steps. The y-axis labels the gradient signal, while the title and grid make the visualization easier to understand and read. This script shows how the chain rule works in a simple neural network. One input passes through two weights to make a prediction, which is compared with the true value using squared error loss. Backpropagation then computes the gradient for each weight, showing how the error signal moves backward through the network. The output includes the prediction, loss, gradients, and a bar chart that helps illustrate this backward flow of responsibility. In a neural network's forward pass, input data moves through each layer to produce a prediction using the model's current weights, biases, and activation functions. No learning or correction happens at this stage. The network simply transforms the inputs into outputs based on its existing parameters. For example, digit images can become probabilities for each digit, while house features can become a predicted price. During a neural network's forward pass, you need to save key intermediate values because they are required later to compute gradients. When training manually with NumPy, this tracking is not automatic, so stored layer inputs, activation outputs, and predictions let the backward pass determine how weights and biases contributed to the loss. Without these saved values, the model can make predictions, but cannot learn effectively from its errors. During training, the network makes predictions in the forward pass and uses a loss function to measure how far they are from the true values. That loss guides the backward pass, which adjusts the model's weights. Repeating this over batches helps the network improve from initially poor predictions to more accurate ones. A decreasing loss suggests the model is learning useful patterns rather than simply memorizing the data. Python code, forward pass. This section demonstrates a single forward pass through a neural network using small mechanical data in NumPy. It also stores the intermediate values needed later to compute gradients. We begin by importing NumPy, a key Python library for efficient array handling and numerical computation. It provides the matrix operations and other tools needed for neural network calculations in this script. To make the code's results consistent, we set NumPy's random number generator to use a fixed seed of 7. This ensures the same random numbers are produced each time the code runs, which makes teaching and debugging easier because the outcomes are predictable. We create a two-dimensional NumPy array to represent two beam examples, each described by two simple features. These sample inputs are used to demonstrate how data moves through the neural network during a forward pass. We scale the input features by dividing each value by the maximum value for its feature across the examples. This normalizes the data to a range from 0 to 1, which helps keep later matrix calculations numerically stable. The first layer is initialized with a 2x3 weight matrix, matching 2 input features and 3 hidden neurons. The weights are drawn from a normal distribution centered at 0, with a standard deviation of 0.3. The layer's biases are set to 0 for all 3 hidden neurons, so the network can learn appropriate bias values during training. The output layer is initialized by creating weights from a normal distribution with mean 0 and standard deviation 0.3. The weight shape matches the 3 hidden neurons connected to one output neuron. The bias is set to 0 for the single output neuron, preparing the network to turn hidden activations into final predictions. Before multiplying matrices in the neural network's forward pass, the code checks that their dimensions are compatible. It confirms that the scaled input can multiply with the first weight matrix, and that the first weight matrix can multiply with the second. These checks help prevent runtime errors and ensure the calculations are valid. To compute the hidden layer's pre-activation values, the scaled input features are multiplied by the first layer's weights, creating a linear transformation. A bias is then added to shift the result and help the model fit the data. These values are the hidden layer's raw outputs before the activation function is applied. The ReLU activation function is applied to the hidden layer's pre-activation values. It keeps positive values unchanged and turns negative values into 0, adding nonlinearity so the model can learn more complex patterns. This is done efficiently across the whole matrix using NumPy's maximum function. The network produces its final predictions by combining the activated hidden layer values with the output layer weights, then adding the output biases. These predicted values are stored for later analysis or backpropagation. The code saves key results from the neural network's forward pass in a cache. These include the scaled input, hidden layer values before and after the ReLU activation, and the final prediction. Storing them makes backpropagation easier because the model can reuse these values to compute gradients and update its parameters. The true target values are small deflections, here represented by the values 0.12 and 0.28. We evaluate the model using mean squared error, which compares predictions to these targets by averaging the squared differences. A lower loss means the predictions are closer to the true values. The output checks key details of a neural network run: the NumPy version, the scaled input shape, the hidden layer activation shape, and the prediction shape. It then shows the rounded predictions and reports the mean squared error to measure how close they are to the true values. Finally, it lists the cached intermediate values needed for later backpropagation or analysis. This script shows a basic forward pass through a small neural network using NumPy. It sets reproducible random values, scales the inputs, initializes weights and biases for a hidden layer and an output layer, then checks that the matrix dimensions match. The network computes hidden values, applies a ReLU activation, produces predictions, and compares them with small target values using mean squared error. It also prints key shapes, rounded predictions, the error, and cached values that could be used later for backpropagation. Backward gradients. Backward gradients show a neural network how to reduce its errors by linking the loss back to specific weights and biases. After the loss is computed, the backward step measures how sensitive that loss is to each parameter, so the network knows what to adjust. Large gradients mean a small parameter change can strongly affect the loss, while small gradients mean the effect is weaker. To compute backward gradients by hand, view the network as a chain of transformations. Backpropagation starts at the output layer, where the loss directly gives the first gradient, then sends that error signal backward through each layer. Each layer adjusts the gradient based on its weights, biases, and any activation function, helping identify which inputs or features most influence the model's prediction. When computing gradients manually in NumPy, the key is to keep array dimensions aligned, so weight, bias, and activation gradients match the layers they belong to. These gradients show how each connection in layer output affects the loss. For batches, gradients are combined to capture the overall training pattern, making neural network learning a clear chain of cause and effect. Python code, backward gradients. Manual gradients make the backward flow of errors easier to see, while a small NumPy network keeps the learning process transparent. Loss curves then provide a simple way to check whether the model may be overfitting. The script begins by importing NumPy for efficient numerical computation and Matplotlib's plotting tools for visualizing data and results. Together, these libraries provide the basic support needed for machine learning work involving both calculations and graphs. We create a NumPy random number generator and seed it with 7, so the same random numbers are produced each time the code runs. This makes the results consistent and repeatable for teaching. We generate 80 sample data points to represent force measurements. These values are drawn randomly from a normal distribution with mean 0 and standard deviation 1, creating realistic variation similar to sensor noise. A second feature is created by sampling values from a standard normal distribution, giving it a different scale from the first feature. The two features are then combined into one two-dimensional dataset, with each row as a sample and each column as a feature. This provides a simple multi-feature dataset for training the neural network. A nonlinear pass or fail target is created by combining force, temperature, and their interaction into a raw score. Scores above 0.2 are labeled as passes, while the rest are labeled as fails. These labels are then converted to 0 or 1 values and shaped as a column for later processing. The dataset is split into training and testing parts. The first 60 samples are used to train the model, and the remaining samples are kept for testing. This lets us evaluate how well the model performs on data it has not seen before. Before running matrix operations, the code checks that the training data has the right dimensions. It confirms there are 60 training samples, each with 2 input features and 1 target value. These checks help catch shape mismatches early and present errors during matrix calculations. The network is initialized with a first layer that connects 2 input features to 4 hidden neurons. Its weights are random values from a normal distribution centered at 0 with a standard deviation of 0.4. The first layer biases are set to 0, with 1 bias for each hidden neuron. The output layer parameters are initialized by creating a weight matrix for the connection from the 4 hidden neurons to 1 output neuron. These weights are randomly drawn from a normal distribution centered at 0, which helps break symmetry so neurons can learn different features. The output bias is initialized to 0, giving the model an extra adjustable term to better fit the data. The sigmoid activation function adds nonlinearity to a neural network by converting an input into a value between 0 and 1. It does this by taking 1 divided by 1 plus the exponential of the negative input. Because its output fits this range, sigmoid is especially useful for binary classification, where results can be interpreted as probabilities. Before training, we set up tracking for the model's performance by storing both training and test loss values. These records make it possible to plot loss curves later and see whether the model is learning well, overfitting, or underfitting. The training loop will run quietly without printing intermediate results, using manually computed backward gradients. The learning rate is set to 0.25, and the model will train for 300 epochs to update and optimize its parameters. Training runs through a set number of epochs. In each pass, the network combines the input features with the first layer's weights and bias to produce the layer's input. It then applies the hyperbolic tangent activation function, adding nonlinearity so the network can learn more complex patterns. The output layer first combines the hidden layer activations with its weights and bias to produce raw scores called logits. Applying the sigmoid function then converts these scores into values between 0 and 1. In binary classification, this lets the model's output be interpreted as the probability of the positive class. A tiny epsilon value is added to keep calculations stable by avoiding division by 0 or the logarithm of 0. The training loss is then computed with cross-entropy, which compares the true labels with the predicted probabilities. Lower cross-entropy loss means the predictions match the labels more closely. In the backward pass, we first find the output layer error by comparing the model's predictions with the target values and normalizing by the number of training samples. Then we compute the second layer's weight gradient using the first layer's activations and the output error. The bias gradient is found by summing the output error across all samples while keeping the dimensions consistent. Backpropagation moves the output error back through the hidden layer to update the first layer weights. The error is first passed backward using the transpose of the output layer weights, then adjusted by the derivative of the hyperbolic tangent activation, which is 1 minus the activation squared. Finally, the input data is combined with this pre-activation gradient to find the weight changes needed to reduce the error. The model updates its parameters using gradients from backpropagation. The first layer bias is adjusted by summing the hidden layer error signals, while the second layer weights and bias are reduced by the learning rate times their gradients. Together, these updates help lower output error and improve the model's predictions. We update the first layer's weights and biases using gradient descent. Each value is adjusted by subtracting the learning rate times its gradient, helping reduce the loss and improve the model's performance. Every 10 epochs, the code records the current training loss to track learning progress. It also processes the test data through the first layer using the hyperbolic tangent activation, preparing it to calculate test loss and check for possible overfitting. The model first uses the sigmoid function to turn the test data's final layer outputs into predicted probabilities. It then measures performance on unseen data with cross-entropy loss, comparing those probabilities with the true test labels. This test loss is saved so the model's performance can be tracked over time. Training predictions are made by comparing each predicted probability with a threshold of 0.5, assigning class 1 to values at or above the threshold, and class 0 to the rest. For test data, the model first computes the hidden layer activations by applying the hyperbolic tangent function to the weighted inputs plus the bias, preparing them for the final prediction step. To evaluate the test data, the model first turns the final layer outputs into predicted probabilities using the sigmoid function. These probabilities are then converted into binary labels. Values at least 0.5 become 1, and lower values become 0. This produces the final test set predictions for later performance evaluation. We evaluate the model by measuring accuracy on both the training and test data. Training accuracy shows how often the model predicts the training labels correctly, while test accuracy shows how well it performs on unseen data. Together, these scores indicate how well the model has learned and generalized. The output summarizes key checks after training a model. It reports the NumPy version for reproducibility, then shows the final training and test losses to compare fit and generalization. It also prints training and test accuracy, followed by the gradient matrix shapes for the first and second layers to confirm the dimensions used in weight updates. This plot compares training and test cross-entropy loss over time during a manual backward gradients training loop. Each point represents a checkpoint every 10 epochs, and the two labeled lines show how performance changes as training progresses. The legend, axis labels, title, and layout make the visualization clear, helping identify possible overfitting by comparing the training and test loss trends. This script uses NumPy to build and train a small two-layer neural network that classifies data from two input features. It learns a nonlinear decision rule through manual backpropagation over 300 training rounds. Training and test losses are tracked to check learning progress and possible overfitting, and the final results report losses and accuracy for both datasets. The loss plot should show improving performance over time and indicate how well the model generalizes to new data. Weight updates. Weight updates are how a neural network improves by adjusting its weights and biases to reduce future prediction errors. In a NumPy training loop, this means using computed gradients to manually change those parameter arrays. The key idea is that errors only help learning when they are converted into specific adjustments that make later predictions more accurate. The learning rate determines how strongly a model updates its weights based on gradients. If it is too low, training can be very slow. If it is too high, the model may overshoot good values and make the loss unstable. Watching the loss over time helps confirm whether updates are improving training. An unpredictable loss may signal a problem with the learning rate or gradient calculations. Weight updates are the core mechanism that connects neural network training to model behavior. Each update slightly changes how the network maps inputs to outputs, and many small changes can produce meaningful learning. However, updates can also lead to overfitting if the model becomes too focused on the training data. A good training loop applies updates consistently, tracks loss, and checks performance on new data to support generalization. Python code, weight updates. Manual updates adjust a neural network's parameters to reduce prediction loss. Gradients indicate the direction that lowers the loss, while the learning rate controls how large each update step is. We import NumPy for efficient numerical work with arrays and mathematical operations, and Matplotlib PyPlot for creating graphs. Together, these libraries provide the basic tools for manipulating data and visualizing trends in the script. We initialize NumPy's default random number generator with a seed of 7, so the same random values are produced each time the code runs. This makes the results repeatable and consistent. We create a simple synthetic dataset by generating 40 evenly spaced input values from 0 to 10 and shaping them for matrix operations. The target values follow a linear pattern where each input is multiplied by 0.8 and increased by 0.6. Random normal noise is then added to make the data resemble imperfect real-world measurements. We calculate the mean and standard deviation of both the input and target data so they can be normalized. This puts the data on a similar scale, which helps keep gradient calculations stable and supports smoother, more reliable training convergence. Before training, both the input data and target data are normalized for stability. Each is centered by subtracting its mean and scaled by dividing by its standard deviation, giving data with an average near 0 and a standard deviation of 1. This helps gradient descent update more reliably and prepares the data for neural network training. Before running matrix operations, the code verifies that both input arrays have the required 40 by 1 shape. This helps ensure the data is properly formatted and prevents shape mismatch errors during neural network training. We initialize a one hidden layer neural network by setting up its hidden layer weights and biases. The weight matrix is filled with random values from a normal distribution centered at 0, with a standard deviation of 0.4, and its shape matches one input feature and 4 hidden neurons. The hidden layer bias is initialized as 4 zeros, so no bias is added at the start. The output layer parameters are initialized by creating a 4 by 1 weight matrix with random values from a normal distribution centered at 0 using a standard deviation of 0.4. This randomness helps break symmetry so the network can learn. The output bias is initialized as a 1 by 1 zero matrix, so it has no initial effect and can be adjusted during training. The training setup uses a learning rate of 0.08 to control how much the model's weights change with each update. It runs for 120 epochs, giving the model repeated chances to reduce error. A loss history is also initialized to record the mean squared error after each epoch and track performance over time. For each training epoch, the network computes the hidden layer input by combining the data with the first layer's weights and adding a bias. It then applies the hyperbolic tangent function, adding nonlinearity so the model can learn more complex patterns. The result is the hidden layer activation. The network makes predictions by combining the hidden layer outputs with the second layer weights and biases. The error is the difference between these predictions and the true target values. To measure overall performance, we square the errors and take their average, producing a single loss value that shows how far the model is from the correct answers. The code records the current loss so model performance can be tracked over time. It then computes the prediction gradient by scaling the error by 2 divided by the number of samples. Finally, it finds the output layer weight gradient by multiplying the transposed hidden activations by the prediction gradients, giving the direction needed to reduce the loss. During backpropagation, the output bias gradient is found by summing the prediction gradients while keeping the shape consistent. The error is then passed back to the hidden layer by multiplying those gradients by the transposed output weights. Finally, the hidden layer gradient is adjusted using the derivative of the hyperbolic tangent activation, preparing it for the next step of backpropagation. To update the network, we first find how the loss changes with the first layer's weights by combining the input data with the hidden layer's gradient. We then find the bias gradient by summing those hidden layer gradients across all samples while keeping the right shape. Finally, the second layer's weights are adjusted by subtracting the learning rate times their gradient, moving them in a direction that reduces the loss. During training, the network updates each bias and weight by moving it opposite the direction of its gradient, scaled by the learning rate. This includes the output layer bias, then the first layer weights and bias. These adjustments reduce loss and help the model make better predictions. To produce predictions in the original units, the model first applies a hyperbolic tangent transformation to the weighted inputs plus bias, creating the hidden layer output. It then uses the second layer's weights and bias to generate scaled predictions. Finally, those predictions are converted back to the target's original scale using the target standard deviation and mean. We evaluate the trained model by comparing its predictions with the actual y values using root mean square error. We also report the NumPy version for reproducibility. Then compare the initial and final loss to show how training reduced the error. Finally, the training error is given in kilonewtons, so the model's accuracy is clear in the original measurement units. This plot visualizes how training loss changes over time. A line chart shows the recorded loss values across epochs, with the x-axis representing training cycles and the y-axis showing mean squared error. The title and grid make the trend easier to interpret, helping confirm whether manual weight updates are reducing the loss during training. This script shows how a simple neural network can learn from synthetic linear data using manual gradient descent updates. The data is normalized, passed through a small hidden layer with a hyperbolic tangent activation, and trained over repeated epochs by reducing mean squared error. As training continues, the loss decreases, showing that the model is fitting the data more closely. Afterward, the root mean square error is measured on the original scale, and the loss curve illustrates the improvement over time. Network diagnosis. Loss curves. A loss curve shows how a neural network's errors change during training. As the model compares its predictions with correct answers, it produces loss values that can be plotted over time. A steadily decreasing loss usually means backpropagation, and the optimizer are helping the model improve, such as learning to classify handwritten digits more accurately. Comparing training loss and validation loss helps show whether a model is truly learning. Training loss measures performance on the data used for learning, while validation loss measures performance on separate data. If both decrease and stay close, the model is likely generalizing well. If training loss falls but validation loss rises, the model may be overfitting and performing poorly on new data. A loss curve helps reveal whether training is working. If loss stays high and flat, the model may not be learning because of issues like the learning rate, data scaling, model design, or labels. If the curve jumps wildly or rises, the learning rate may be too high, while a slow decline may mean training needs more time or better pre-processing. Reading these patterns helps you judge whether a model is learning meaningful patterns before deployment. Python code, loss curves. Loss curves show how a neural network is learning, while validation loss helps reveal when the model may be overfitting. This example focuses on computing gradients manually with NumPy. The script imports NumPy for efficient numerical work with arrays and Matplotlib pyplot for creating plots. Together, these libraries provide the basic tools for data manipulation and visualization. We set NumPy's random number generator to use a seed value of 7. This makes future random results repeatable each time the script runs, which helps with reproducibility and debugging. We create a simulated mechanical sensor dataset with 180 samples and 2 features. The data is generated as normally distributed random values, forming a sensor reading matrix that can be used for later analysis and model training. We create binary labels by applying a noisy linear rule to the features. Random noise is added to a weighted combination of the first 2 features, where the first feature has a positive influence and the second has a negative one. If the resulting value is greater than 0, the label is 1. Otherwise, it is 0. This simulates classification with a noisy linear decision boundary. The dataset is divided into training and validation portions. The first 120 samples are used for training, and the remaining samples are kept for validation, with features and labels split in the same way so they stay aligned. This lets the model learn from one part of the data and be evaluated on another to check how well it generalizes. We first check that the training data has 120 rows and 2 columns, confirming the data was prepared correctly. We then make sure the validation data has the same number of columns, so both datasets are compatible for neural network processing. Standardize the data by first finding the training set's feature-wise mean and standard deviation, with a small constant added to avoid division by 0. Use these training statistics to center and scale the training data, so it has 0 mean and unit variance. Then apply the same transformation to the validation data to keep pre-processing consistent and prevent data leakage. We manually set up a small neural network with 6 hidden neurons. The weights from the input layer to the hidden layer and from the hidden layer to the output layer are initialized with small random values scaled by 0.3. The hidden and output biases are initialized to 0, with dimensions matching their respective layers. The sigmoid function transforms an input into a value between 0 and 1, which is useful for binary classification in neural networks. To keep the calculation stable, the input is first limited to the range from -30 to 30. It then uses the exponential function to produce the standard sigmoid output, avoiding overflow or underflow from extreme values. The binary loss function measures binary cross-entropy between the true labels and predicted probabilities. It uses a small safety value to avoid taking the logarithm of 0, then averages the negative log likelihood across all examples. This loss is lower when predicted probabilities match the true labels more closely. The training setup uses 160 epochs, meaning the model will pass through the training data that many times. A learning rate of 0.08 sets the optimization step size. Training and validation losses are also recorded over time, so performance can be monitored and issues like overfitting can be detected. Training runs for a fixed number of epochs, repeating the process over the dataset. In each pass, the network computes the hidden layer by combining the input data with the first weights and bias, then applying the hyperbolic tangent function for nonlinearity. It then uses those hidden activations with the second weights and bias, applies the sigmoid function, and produces flattened predicted probabilities for further processing. Backpropagation starts by measuring the prediction error as the difference between the model's outputs and the true labels. This error is used to compute the average gradients for the second layer's weights and biases. The error is then passed backward through the second layer and adjusted by the derivative of the hyperbolic tangent activation, giving the gradient needed to update the first layer's parameters. Backpropagation computes how the loss changes with each parameter, then uses those gradients to improve the model. For the first layer, the weight gradient comes from combining the training data with the backpropagated error and averaging over all samples, while the bias gradient is the average error across samples. The second layer's weights and biases are then updated by subtracting the learning rate times their gradients, helping reduce the loss. The code performs a gradient descent update by adjusting the first layer's weights and biases using the learning rate and computed gradients. It then calculates the training loss with a binary loss function and stores it for later review. Finally, it evaluates the validation data by passing the standardized features through the network, using tanh in the first layer and sigmoid in the second layer to produce predicted probabilities for unseen examples. The code records the validation loss for each training epoch by comparing the true validation labels with the model's predicted probabilities. This helps track how well the model performs on unseen data and can reveal signs of overfitting. To find validation accuracy, convert each predicted probability into a binary label using 0.5 as the cutoff. Then compare these predicted labels with the true validation labels and take the average of the correct matches. This gives the share of validation samples the model classified correctly. The code reports the NumPy version, then summarizes model performance by printing the final training loss, validation loss, and validation accuracy. These values show how well the model fits the training data and how well it performs on unseen data. It also warns that a large gap between training and validation loss may indicate overfitting. This plot visualizes model performance during training by showing both training and validation loss across epochs. The axes identify the epoch number and binary cross-entropy loss, while the title, legend, and grid make the loss curves easier to interpret. This script trains a small neural network in NumPy using manual backpropagation. It creates a synthetic binary classification dataset, standardizes the features, and trains a one hidden layer model with gradient descent while tracking training and validation loss. After training, it reports validation accuracy and final losses, then plots the loss curves to show learning progress and reveal possible overfitting from gaps between training and validation performance. Loss curve checks. Loss curve checks show whether a neural network is truly learning or simply memorizing the training data. A falling training loss means the optimizer is improving the model, but validation loss is needed to judge performance on new data. When both training and validation loss decrease and settle at low levels, the model is more likely to generalize well. A widening gap between training loss and validation loss usually signals overfitting, where the model learns the training data too closely and performs poorly on new data. Common fixes include stopping training earlier, adding more data, using regularization or data augmentation, or simplifying the model. If both losses remain high, the model may be underfitting because it is too simple, poorly tuned, or working with weak features or preprocessing. Loss curves help diagnose whether a model is training properly. Wild fluctuations can mean the learning rate is too high, while very slow improvement may suggest it is too low or the model is a poor fit. Sudden spikes can point to data problems or numerical instability. Use the curve to decide whether to adjust the data, model architecture, or optimization settings. Python code, loss curve checks. Use loss curves to diagnose how a model is learning by comparing training and validation behavior. This helps reveal whether the model is improving, overfitting, or failing to generalize. Manual gradients with NumPy can support this process by making the learning updates more transparent. The script begins by importing NumPy for efficient numerical work with arrays and mathematical operations. It also imports Matplotlib's plotting tools to create visualizations. Together, these libraries provide the basic tools for data handling and plotting in Python. To make results consistent and reproducible, we initialize NumPy's random number generator with a fixed seed of 7. This ensures the same random sequence is produced each time the code runs, which helps with debugging and comparing results across runs. We create a simulated mechanical sensor dataset with 160 samples. The readings are drawn uniformly from -3 to +3, giving a broad range of possible sensor values. The data is stored as a two-dimensional array, with one column representing a single input feature. To simulate a nonlinear vibration response, we add small, normally distributed noise to a model that combines a sine wave with a linear trend. The noise is centered at 0 with a modest spread, creating realistic variation like the imperfections found in measured data. To create training and validation sets, first shuffle the sample indices using NumPy's permutation function. Use the first 110 shuffled indices for training and the rest for validation. This gives two random, non-overlapping sets. The training data is standardized by using its mean to center the values and its standard deviation to scale them, with a small constant added to avoid division by 0. The same transformation is then applied to the dataset, producing values with roughly 0 mean and unit standard deviation. This scaling helps the model train more effectively. We prepare the training and validation data by selecting the scaled input features and matching target values for each set of indices. The training set is used to teach the model with standardized inputs, while the validation set is kept separate to evaluate performance on unseen data. Using the same indices for inputs and targets keeps each example correctly aligned. Before training begins, the code checks that the training inputs and targets have the same number of samples, and does the same for the validation data. This confirms that each input is matched with the correct output, helping prevent alignment errors during training. This setup creates a simple neural network with one hidden layer containing 12 neurons. The first layer's weights are randomly initialized from a normal distribution centered at 0, with a moderate spread, and shaped to connect one input to the 12 hidden neurons. The hidden layer biases are initialized to 0, so the neurons start with no added bias. The output layer parameters are initialized by creating a weight matrix with random values from a normal distribution centered at 0, using a standard deviation of 0.4. Its size connects the hidden units to a single output. The output bias is initialized to 0, giving the model added flexibility when fitting the data. The training setup uses 220 epochs, meaning the model will pass through the training data that many times. A learning rate of 0.035 sets the optimization step size. Training and validation losses are recorded over time, so the model's learning behavior can be monitored and compared across both datasets. Training runs through each epoch, using the current model parameters to make predictions. In the forward pass, the training data is combined with the first weights and bias, then passed through the hyperbolic tangent activation to produce hidden layer activations. These activations are then combined with the second weights and bias to generate the model's predictions. To track training performance, we compare the model's predictions with the actual training values to find the errors. We then square those errors and average them to get the training loss, which summarizes how well the model fits the training data. This loss is saved after each epoch, so we can monitor learning progress over time. To backpropagate through the second layer, we first scale the prediction error by multiplying it by 2 and dividing by the number of training samples. This gives the gradient with respect to the predictions. We then use the hidden layer activations and this gradient to compute how the second layer weights should change. Finally, we sum the prediction gradients across all samples to find the bias gradient, so the biases can be updated to reduce the loss. Backpropagation through the hidden layer starts by finding how the loss changes with the hidden activations, using the prediction gradient and the output layer weights. This is then converted into a gradient for the hidden layer's pre-activation values by applying the derivative of the hyperbolic tangent function. Finally, the hidden layer weight gradient is found by combining the training inputs with this pre-activation gradient, giving the update needed to reduce the loss during training. During backpropagation, the model sums the bias gradients for the first layer across all samples while keeping the shape consistent. It then updates the second layer's weights and bias by subtracting the learning rate times their gradients. These steps help reduce the loss function. The model updates the first layer's weights and biases using gradient descent, moving them in the direction that reduces loss. It then applies the hyperbolic tangent function to compute hidden layer activations for the validation data. Finally, it uses the second layer to generate validation predictions, helping assess performance on unseen data. To evaluate performance on unseen data, we compare the model's validation predictions with the actual targets to find the validation error. We then average the squared errors to get the validation loss, using mean squared error as a single performance measure. This loss is saved each epoch, so we can track how the model learns over time. To summarize learning behavior, identify the epoch with the lowest validation loss, adjusting the index so it matches normal epoch numbering. Then compare the final validation loss with the final training loss to estimate the generalization gap. Finally, report the NumPy version to support reproducibility and debugging. After training, we report the final training loss and final validation loss. each rounded to 4 decimal places, to show how the model performed on both the training data and unseen data. We also identify the epoch with the lowest validation loss, which marks the model's best validation performance and helps diagnose its learning behavior. Compare the final training and validation losses to judge model behavior. A large gap, above 0.08, suggests overfitting, while a final validation loss still above 85% of its starting value suggests weak learning or underfitting. If neither condition holds, the model likely shows reasonable generalization to unseen data. The code prints a short diagnostic message based on the loss curve analysis. It summarizes whether the model appears to be overfitting, underfitting, or generalizing well by comparing training and validation loss. Create a clear plot of training and validation loss across epochs to evaluate model learning. The training loss shows how well the model fits the training data, while the validation loss shows how well it generalizes to unseen data. Comparing both curves helps diagnose the model's learning behavior over time. The plot marks the best validation point with a gray dashed vertical line, making it easier to see when validation performance peaked. The axes label training progress by epoch and track mean squared error, while the title clarifies that the loss curves are being used to diagnose network behavior over time. The plot is finalized by adding a legend to distinguish training and validation loss, turning on a lightly transparent grid for easier reading, and adjusting the layout so elements do not overlap. Displaying the plot then lets us compare the loss curves across epochs and evaluate the model's training performance. This script trains a small, one-hidden-layer neural network on synthetic mechanical sensor data. It standardizes the inputs, splits the data into training and validation sets, and uses manual backpropagation to reduce mean squared error over many epochs. After training, it reports the final losses, finds the best validation epoch, and judges whether the model is overfitting, learning weakly, or generalizing reasonably. It also plots the training and validation loss curves to support this diagnosis. Test metrics. Test metrics show how well a neural network performs on new data, not just how its loss changes during training. For classification, accuracy can be misleading when classes are imbalanced, so precision and recall help reveal false alarms and missed cases. For regression, metrics measure how large prediction errors are. The right metric should match the task and reflect the real impact of mistakes. Keep the test set separate until final evaluation so it reflects how the model performs on new data. Tune choices like learning rate or model architecture using only training and validation results. If the test set is used too early, especially with neural networks, the model can overfit to its specific quirks, making test metrics less reliable as a guide to real-world performance. Test metrics help reveal overfitting, underfitting, and whether model comparisons are fair. Strong training results with weak test results suggest the model may be learning irrelevant details, while weak results on both can point to underfitting or problems with features or training. By comparing metrics across datasets, you can diagnose issues and judge whether the model is reliable enough for deployment. Python code, test metrics. Test metrics show how well a network performs on unseen data. Training manually with NumPy makes the gradients easier to inspect, while gaps in loss help reveal possible overfitting. The script imports NumPy for numerical work with arrays and matrices, and Matplotlib's plotting tools for creating graphs and charts. Together, these libraries provide the basic tools for data manipulation and visualization. We initialize NumPy's default random number generator with a seed of 7, so the same random values are produced each time the code runs. This makes the results consistent and repeatable. A small classification dataset is created with 240 samples, each containing 2 features. The feature values are generated randomly from a normal distribution with mean 0 and standard deviation 1, giving a simple controlled dataset for testing classification models. We add random noise with mean 0 and a small standard deviation to make the labels less perfectly predictable. The labels are then created using a nonlinear rule based on the first feature squared, plus a scaled version of the second feature, plus the noise. Samples above a chosen threshold are labeled 1, and the rest are labeled 0, creating a simulated classification task with a nonlinear decision boundary. To split the dataset, first, shuffle the sample indices randomly using NumPy's random permutation function. Then use 140 samples for training, 50 for validation, and 50 for testing. This creates separate data groups for learning, tuning hyperparameters, and evaluating performance on unseen data. To standardize features, first compute the mean and standard deviation using only the training data to avoid data leakage. Then scale the data by subtracting the mean and dividing by the standard deviation, with a small constant added to prevent division by 0. This centers the features around 0 and gives them unit variance, which often helps machine learning algorithms train more effectively. To evaluate the model fairly, the data is split into training, validation, and test sets. The training set is used for learning. The validation set helps tune the model and reduce overfitting, and the test set is kept separate to measure performance on unseen data. This validation checks that the training data has the correct number of features and that the test labels match the number of test samples. It helps catch data preparation mismatches before model training or evaluation begins. We set up a simple neural network by choosing 8 neurons for the hidden layer. The first layer's weights are initialized from a normal distribution centered at 0 with a standard deviation of 0.5, sized to connect the input features to the hidden neurons. The hidden layer biases are initialized to 0. The output layer is initialized with a weight matrix and a bias. The weights are drawn from a normal distribution centered at 0 with a standard deviation of 0.5, sized to connect the hidden units to one output. The bias is a single 0 value, giving the network a starting point for learning the final transformation. This function implements a numerically stable sigmoid activation for neural networks. It first limits the input to a safe range, then maps it to a value between 0 and 1. This makes it useful for binary classification while avoiding overflow from extreme input values. The forward function calculates a model's predictions for a batch of inputs. It first creates hidden layer activations by combining the inputs with the first weights and bias, then applying the hyperbolic tangent function. It then uses those activations with the second weights and bias and applies the sigmoid function to produce output probabilities. The function returns both the hidden activations and the final probabilities. This function computes the average binary cross-entropy loss to measure how well a classification model predicts true labels. It first keeps predicted probabilities away from 0 and 1 to avoid logarithm errors, then averages the negative log likelihood across all examples. The result is one scalar value representing the model's prediction error. Set the learning rate to 0.08 and train for 220 epochs. The learning rate controls the size of each parameter update, while the epochs determine how many times the model sees the full training dataset. Track both training and validation loss over time to monitor performance and help identify issues such as overfitting. Training runs through a set number of epochs, repeating the main learning steps each time. In each epoch, the network performs a forward pass on the training data to compute hidden activations and predicted probabilities. It then compares those predictions with the true labels to calculate the error, shaping it correctly for backpropagation. This error guides later weight updates, so the network can improve over time. To update the output layer, the model computes average gradients for its weights and bias from the current error. The weight gradient comes from combining the hidden layer activations with the error across all training samples, while the bias gradient is the average error. These gradients guide how the weights and biases are adjusted so the model can learn from its mistakes. Backpropagation continues by finding the hidden layer gradient, which carries the output error backward through the network. The error is combined with the hidden to output weights and adjusted by the derivative of the hyperbolic tangent activation. Then, the input to hidden weight gradient is computed as an average over the training samples, and the hidden bias gradient is found by averaging the hidden layer gradients. These values are then ready to update the model during training. The code uses gradient descent to update the neural network's parameters. It adjusts the weights and biases in both the output and hidden layers by subtracting the learning rate times their gradients. Repeating this process helps refine the model and reduce the loss. After each pass, we record the training and validation losses by comparing the true labels with the model's predicted probabilities using binary cross-entropy. Tracking these losses over time shows how the model is learning and helps identify problems such as overfitting. The metrics function computes basic classification results without external libraries. It turns predicted probabilities into 0 or 1 labels using a threshold of 1/2, then counts cases such as true positives and false positives. These counts provide the basis for later metrics like precision and recall. False negatives are the cases where the model predicts 0 even though the true label is 1. True negatives are the cases where both the prediction and the true label are 0. Accuracy, precision, and recall summarize different parts of a model's classification performance. Accuracy measures the share of all predictions that are correct. Precision measures how many predicted positives are truly positive, while recall measures how many actual positives the model successfully finds. Together, these metrics provide a concise basis for evaluating the model. To evaluate the model, we test it on data that was not used during training or validation. The model makes predictions for the test features, and we compare them with the true labels to measure accuracy, precision, and recall. These results show how well the model performs on new, unseen data. The code measures both training and validation accuracy by comparing the true labels with the model's predicted probabilities. Training accuracy shows how well the model fits the data it learned from, while validation accuracy shows how well it performs on separate data. Comparing the two helps reveal whether the model is overfitting or generalizing well. The output reports key information for checking the model and its results. It first shows the NumPy version for reproducibility, then summarizes final training and validation loss and accuracy to show fit and generalization during training. It also reports test accuracy, precision, and recall, giving a concise view of performance on unseen data and how well positive predictions are identified. Create a clear plot of training and validation loss across epochs. The training loss shows how the model improves on the data it learns from, while the validation loss shows how well it performs on unseen data. Comparing the two curves helps reveal whether the model is generalizing well or starting to overfit. The plot is formatted to show model loss over training. The x-axis is labeled by epoch, the y-axis shows binary cross-entropy loss, and the title explains that these loss curves are reviewed before final test metrics. A legend distinguishes the training and validation curves, so the results are easier to interpret. Matplotlib adjusts the plot layout so all elements fit neatly within the figure. The tight layout function handles spacing automatically, and the show function displays the final plot. This lets us visually compare the training and validation loss curves. This script builds a small neural network from scratch with NumPy to classify synthetic data separated by a nonlinear boundary. It creates and standardizes the data, trains a one-hidden layer model with sigmoid activation using gradient descent, and tracks training and validation loss to watch for overfitting. After training, it evaluates the model on a test set using accuracy, precision, and recall, then plots the loss curves to show how well the model learned and generalized. In this lecture, you learn to explain backpropagation as distributing output error backward through network layers, implement a simple neural network training loop with manual gradients and NumPy, and analyze neural network learning using loss curves, test metrics, and overfitting checks. In the next module, Module 8, we will go over none. Thank you for your attention. See you all in the next lecture.